We have lesson 6, fitting and using least squares regression line. Okay, so let's get started on this. So, here we go. Learning objectives is we'll look at significant figures first. Okay, we're going to look at calculating the least squares regression line using our class pad and interpreting the slope of the line in terms of the context of the question. Lastly, making predictions based on whether it's interpolation or extrapolation to see the reliability of any prediction. Okay, significant figures. You would have done significant figures before, okay, so they are in relationship to working left to right on the number, okay, it's all about the first non-zero, okay, so we'll see some examples of this in a second. As you then work across, as you're counting how many significant figures you want to, in fact, be rounding to. Before the decimal point, in other words, to the left, right, 2, 4, 5, 8, every single one of these is significant. Our first significant number here is going to be the 2. And our second significant number here is going to be the 4. So we're actually going to be rounding this one to the nearest 100. Okay, so 2, 4, 5, 8. So we're rounding this second significant figure. So answer for that is in fact going to be 2,500. Next one is we have 12.5206. We're going to round it to 3 significant figures. Here's our first, here's our second, here's our third. So basically this is to 1 decimal point, and we end up with our solution there of 12.5. Next one, rounding to 2 significant figures. So all of these zeros at the start are non-significant, so we don't reach a significant figure until the 3. Then we have the 7, so we're rounding the 7, and that will round up to an 8. Keep the zeros at the start. Okay, there's some practice questions here, so if you want to pause here, you can, to try and give these ones a go, rounding to 3 significant figures, similar to the last ones we just did. Right, so here's some solutions come through, so you can go through and check those ones if you want. For question F, if you had 0.0041, you probably should put the 0 as well. And the last one here will tend to get some people as well. It's 46.0. After the decimal point, the zeros become significant. All right, so before they may not consider to be significant, possibly not, they still could be. But after the decimal point, they would be counted as significant. So that's in relationship to question G there. All right, so now looking at the linear regression. All right, so this is what we're going to be able to do. We're creating an equation in terms of y is equal to ax plus b. All right, and it's going to help us make some predictions. In a calc free, we would be expected to do this as a eyeball method, and we'll give this a go in a second. Let's say we had these dots, okay, we would want to try and best fit a line that matches to the graph here. Here is 1, here is 2, here is 3, and here is 4. A few things you notice is it doesn't need to go through the first and last dot. Sometimes students make this idea that it has to go through the last dot or it has to go through the first dot. It doesn't have to at all, all right, so don't do that. The other thing is that they sometimes think it has to go through the origin as well, but it doesn't, so don't make it go through the origin, all right? The one thing I would do is I would extend these red lines a little bit further beyond where they currently are, all the way through to the y-axis and all the way through to wherever they need to go, maybe the end of the graph, possibly. All right. You may have something slightly different to the person next to you. It's perfectly fine, but yeah, it should be pretty similar. So there is some leniency in terms of calc free here, in terms of your line, but you want to have it reasonably accurate. We're going to look at how to do this in terms of our class pad now. A lot of data entry, okay, and just using your regression values that we did before. Right, so there's some extra information there about outliers, association must exist, and numeric data, which is fairly self-explanatory. Okay, least squares regression lines. So if we consider the scatter plot below, what we're aiming to do, and we get onto this a little bit later as well, is talking about the residuals here. Okay, you don't need to know this formula. Your class pad will do all the calculations for you. But just so you can start to see, what we have is these blue arrows are indicating the residuals. In other words, it's the difference between the estimated line and the dot, or the actual data point itself. Okay, so it's a vertical calculation between the dot and the green line, as you can see those blue values there. Right, we call those residuals. We don't need to know this formula at all, so don't worry about that. If we added an extra point in, we could see how this would then change. So now the line of best fit would be changed, and your residuals would be slightly different as well. Okay, so now we're going to have a quick go at how to do this on our class pad. All right, so we're going to put this in this form here. Y is equal to ax plus b. Y is the response variable, so on that vertical axis. X is the explanatory variable on the horizontal axis. A is the gradient or the slope. B is the y-intercept. We probably want to round to 4 decimal places, okay, unless otherwise told so. Okay, so keep that in mind. And obviously we should know now how to identify the explanatory and the response variable. All right, so here's a set of data. Okay, so we've got height against weight. First thing is we've got to input the data. Okay, so previously what we did is we actually put this in terms of a scatter graph. I wouldn't worry about labeling the two. Don't worry about that. That's probably take you too long. Okay, and you could in fact plot this as a scatter plot as we did earlier on. This doesn't really help you that much. Okay, we actually want to do some calculations, all right, as opposed to just draw it. Okay, so what we want to now do is we want to now go to the calc, regression, and linear regression. All right, and as you do that is we then started last week to get into the habit of copying the formula into y1, or in this case it's showing y6. It shouldn't actually matter. And the residual, I sometimes would then start to turn that to list 3. Once you hit OK, it then generates your line of best fit. Okay, so you can see 0.86729, all right, rounding to 4 decimal points, and your B value is negative 84.82316, again rounding to 4 decimal points. You can see your R value, which we've spoken about, and you can see your R squared value as well. Okay, so the first 4 things are the things that we are mainly concerned with here. As you then click OK, it draws it for you. So over on the right, you can see it has sketched it for you there, which is pretty good. And then you should be able to transfer that sketch across to your own drawing as well. All right, so then we could write our equation of our line here like so, 0.867x minus 84.8. Right, there's the first half of the exercise. You can stop here and you can give that a go if you want, but I'm going to keep going with the remainder of this video. All right, so using the least squares on the regression line or interpreting it. All right, 2 ways. Interpret the slope and intercept within the context of the question and to make, predictions. Okay, so we're going to have a look at both of these. They will definitely come up in tests and exams, so you need to understand how to do both of them. So here's our next example, all right, where there's an association of the second-hand car and its age. Okay, we've looked at this example a few times already. So we've got the age of the different cars and the price of those cars in dollars. Identify the explanatory and the response. And as we can see, we can start to see a pretty strong negative association between the two variables. All right, from our class pad, the R value is 0.964, it's a negative, sorry, indicating it is a negative. Therefore, it's a strong negative linear association between the two variables. Okay, next what I do is fit the least squares regression line, calculate the equation, interpret the slope, and the intercept. So from our class pad is that we should have been able to generate 2 points. Okay, so the first thing that we've done here is we've tried to generate the y-intercept as 1 point. So the reason why we're doing this is to get one coordinate. So what this equation is at the top is actually the equation of the least squares regression line when you would put it into your class pad as we did in the earlier example. Then we need to find 2 points in order to draw the line. So what we're doing here is we're substituting one of the points for x is 0 to generate 35,100. So what that's actually going to do on the graph here is it's actually going to be able to put a dot at 35,100. Immediately you can say, well, that's probably where I would have started this line of best fit anyway. Then what I would do is I would substitute a point which is later over on the higher ends of the x values. So in this case, we're using x is equal to 8 and substitute it in. And what do you get? 3,580. And you could give that a go at plotting that as well. Now you've got your 2 points, as you could extend the line between the two and possibly past and beyond. All right, so we've got our line of best fit. Now we want to interpret the slope. 2 parts to this in terms of the interpreting. So the negative 3940 tells us that the price of the cars decreases by 3,940 each year. Right, so for every 1 year it increases in age, what happens is it goes down by 3,940. The other thing is that it's saying that these new cars, the intercept 35,100 tells that the price of the car when it is age 0, or in other words, when it is new. Okay, so that's really relating it to the context of the question there as well. So if the new car cost is 35,100, okay, and obviously it is depreciating at that 3,940 each year. So there's a sentence which you could then start to use as similar to our coefficient of determination. So the slope is the average change. It could be an increase or it could be a decrease. We saw a decrease in that last example. In the response variable, or y, whatever that would be, for every 1 unit increase in the explanatory variable. All right, so it would always be for every 1 unit increase in the explanatory. We'll see another example in a moment. The y-intercept is the average value of the response variable where the explanatory variable is equated to 0. So as we just looked at with that car example, it was 35,100. Okay, it's not exact because it's based off data and data points, but it's just an estimation. Here's a nice model, okay, which we could possibly use to assist you with answering these questions or interpreting these slope/y-intercepts. Okay. We will now want to create a prediction for a car that is 5.5 years old. All right, so using the graph, we could go up from the graph and then estimate across and make an estimation there, which would be approximately 13,000. There's probably some leniency here because if your line was ever so slightly angled differently, you would give a different result, as opposed to if it was a bit steeper. But if you've calculated 2 points correctly at the start, like what we did, you should be able to get it reasonably accurate here. Using the equation, all right, is that we substituted in 5.5, okay, and there's the exact answer, 13,430. So that would be more as a calc assumed, whereas using the graph would be more as a calc free question. All right, so if you were asked to do that, they might be divided into those 2 different ways. All right, try not, unless the question says otherwise, but in a calc assumed, I would probably try and be the more accurate one, which was the second one there. Okay, and as we said, using the equation is more preferable. All right, side note, making predictions in general. Let's have a quick look. Here is some data, time, and then their mark, or time spent studying, and their marks associated with that. All right, if we fitted and inputted this stuff or this data into our stats, and we would generate this line of best fit, 1.62t plus 30.8. Okay, then we could go and make a prediction. Let's say, for example, 8 hours of studying would obtain a mark of, all right, substitute that 8 in, and you generate with 43.76 as an estimation. Okay, and because all the numbers are rounded to whole numbers, maybe it'd be okay to round to 44% there. 12 hours of studying would obtain a mark of 50, etc., etc. We have limitations here. 80 hours of studying would obtain a mark of 160%, but obviously we know that's theoretically not possible. So this then gets us on to our next idea of predictions. Because in that last example, if you studied 80 hours, it should be predicted that you get 160%. So what happens is that this generates this idea that when we predict outside the data range, right, it becomes less reliable. Okay, so the maximum study time was 36 hours, yet we were trying to predict for someone who may in fact do 80 hours of study. Okay, so this process of making predictions within the range is called interpolation, and it's much more reliable. All right, so interpolating is a reason for reliability, and commenting or making predictions outside the range is called extrapolation, and that's much less reliable. All right, so our little note there is to be confident in the prediction, it needs to be interpolation and have a strong relationship and be linear. If any of the above aren't true, we need to say that the prediction is not reliable. Okay, most of the time it will be a strong relationship. It may be interpolation or extrapolation, so you could actually comment on, yes, it is a strong relationship, however, you are extrapolating, which might give it some less confidence in your prediction or the reliability of your prediction. All right, so here's some examples of interpolation. So you can see the last blue data point there between the two arrows. All right, that's the last data point. So interpolation would be between that and all the other data points, whereas extrapolation would be beyond that. Okay, doesn't have to be far beyond that, but as long as it's beyond it, it's called extrapolating. Once again, you can see some examples there. Interpolation prediction would be the 5.5, like what we did. Extrapolation for that example might be when the age of the car is 10 years old. All right, so the extrapolation of the car at 10 years old would be much less reliable in comparison to the 5.5 years old. And in fact, it would give you a negative value, which means that it's not possible at all. All right, calculate and interpret the coefficient determination. As a reminder, if we had R, which was negative 0.964, coefficient of determination would generate a positive value there. So the 93% variation in the price of the second-hand cars can be explained by the variation in the age of the cars. So we did that in our last lesson. So as a guide, any relationship with the coefficient of determination above 30% can be regarded as having significant predictive behavior. This one is way above 30%, which indicates it has some predictive power there. Okay, and that is it. Good luck with the exercise.